So I've pre-written code, first of all, that's going to print off another table here. But before we get into the table, let's just go back into the code. And I'm going to use it like a little scratch pad here for a second. We've dealt with numeric data types, but we've only dealt with whole numbers. We've dealt with integers thus far. We've seen that integers can be like, I don't know, negative 789. They can be 0, or they can be like 456. But they're all whole numbers. And so the next series of data types that I want to go over is going to be what they call floating point data types, where you can have a decimal involved, like 3.1415926, for instance. Now let's jump into our table and look at some of the data types, and then we see that, well, there's 3 as opposed to the 8 that were just integers. And the 3 types are, well, the float type, the double type, and the long double. And like the integers, each of these types, well, use more and more resources. And so the float consumes 4 bytes, the double 8, and the long double 16 bytes. Now, what are these columns here? And so let's jump back into our little scratch pad here for a second and explain something about floating point data types if you weren't aware. And so you can have a fraction, say like 1.23, and we would say that this decimal here has 2 decimal places of precision because, well, there's a decimal point and then, well, there's 2 decimal places of precision afterwards. And if we were to add another couple to make this a fraction more precise, well, now we have 4 decimal places of precision, and likewise, we can have 6 places, or we can have 8 places, or whatever, and make our number more and more precise here. Now, that's what the next column is sort of all about, is the level of precision that each of these data types is capable of obtaining. And so for a float, for instance, you can get 38 places of precision. Now, already, that is a pretty precise decimal place there. So, for instance, that might be like 1 point, and then, well, 38 places of precision. So there's 9, there's 18, there's 27, there's 36, and there is 38. So this lends itself to a lot of precision already that you can deal with just a float. And then when we run our table again, we can see that it gets more precise from there. The double, for instance, can have 308 levels of precision, and the long double, well, almost 5,000. So that's pretty ridiculous. You might use this long double if you were dealing with atoms and molecules or something, and this float would be for like just about everything. You rarely need to get this precise, but the float is capable of it. Now, for this column, the one that's labeled max here, well, what does all these numbers mean? So there's something called scientific notation. You might be familiar with it, but for those of you that are not, a quick lesson in scientific notation. We can take a, say, pretty small number, like 1,000 or something, and, well, let's say 1,234, just to illustrate a point a little bit more clearly. Well, this would actually just be 1,234.0. It's the same number here. And a different way that you can write this out in scientific notation, that is 1.234 times 10 to the third. And so what does this 10 to the third business mean? Well, we've basically taken this decimal point right there, and we've moved it over 1, 2, 3 spots to make this a fraction here, 1.234. And so this right here is just how many times we moved over that decimal place to represent our number in scientific notation. And so that's just, once again, just the number of times we moved our decimal place over. Well, a different way that you can type out 1.234 times 10 to the third is like this. You can say 1.234 and then put an E and then say plus 3. And so this means the same thing as the line above it. It's just a different way of typing it out. And so let's get rid of all of this stuff and let's run our table again. And we see that same notation here. We see some sort of fraction, some sort of decimal point number. And then we see this e plus 38. Well, that's just 38 times that decimal point was moved over. And so essentially you can have a number that is like 1 and then have 38 digits essentially after that, however many this is because I'm not counting this time. And so you can have a pretty big number, and I don't know if this is 38 places, I'm just guessing here once again, but we can move this number, this decimal place over 38 times and rewrite this as 1.234 times 10 to the 38, right? Same thing, you know? And so that's basically what we're representing in this last bit of the table. When we run this, we see that we can put a number with 38 digits in it in our float. And for the double, well, 308 digits. And for the long double, well, goodness gracious, almost 5,000 digits. These are big, big numbers. And so that's the table in a nutshell. That's the float double and long double explained, how much memory they consume, the level of precision that you can get out of each of these, and how big the number can be out of each of these, essentially. And so, all of that being said, if you just wanted to use them, they're just like using integers, where we took this int apples and we gave it a value and then we started using it in our program. Well, if you wanted to use a float, well, you just type out the keyword float, name it something, and then give it some sort of value here, right? And if same thing for a double, for instance, you know, double name, and then we give it some sort of a value, but this one can be a much bigger value. And same thing with the long double. So this is just examples of how to use all of these, and then you just run it like this, you know, so easy enough. Now to explain the table, once again, this is sort of like the integers, where depending on your system and depending on, you know, which IDE you're using, which compiler you're using, there's different considerations that go into this, but you may get different values. And so than I got here. And so I just want to show you how you can get these values on your own for your system, so that you can work with these. If you're, you know, not sure that a float will cut it, you know, maybe you need to use a double here. And so instead of the C limits library, well, I've included up top this C float library that does some very similar things that the C limits did for us, with explaining the mins and maxes of your particular system. And, you know, you just see out this stuff to the screen. These right here, this float min and float max and double min and double max and long double min and long double max. Well, these are just the keywords that you can use from within this C float library. And if you want to see them, you can just, easy enough, just see out what is the float min. This is basically how precise can I make a float here, and then just drop it down a line. And that would be how you would use it in your own code. And for the size and bytes that each of these consume in resources, we just use the same old size of guy that we've been using, just putting float double and long double in the parentheses. And so that should pretty much sum everything up here as far as a basic intro goes. There's a lot more to floats that we'll encounter in the future, but I think it would be more appropriate to tackle the rest of the information about these floats later. This will get you up and running, though. All right, hope you enjoyed it. See you in the next one.